Hi, my name is Garima Bhatia, and today we're going to talk about the concept of rationalizability in game theory. Rationalizability, in a sense, is a solution concept in which we try to find the best responses of players in a game under the assumption of rationality. What this means is that a player's action is considered rational if it maximizes her payoff given some belief about the other player's actions. So in any scenario, a player would only play a response that gives her the maximum payoff. This is intuitive because we all like to maximize our utility or our payoff in any game or in any scenario. So given some belief that a player has about the other player, a person's best response is the one that gives her the maximum benefit or the maximum return out of the game. In rationalizability, some of the important assumptions that are taken into consideration and are listed on the slide here. So, for example, in a two-player game, the assumptions that we make for rationalizability are that player one knows that the other player or player two is rational. On the other hand, player two also knows that player one is rational. Player 2 knows that player 1 knows that she is rational, and so on to ad infinitum. So this keeps going on, that each player assumes that the other player knows that the other player knows that she is rational, and we can keep continuing this. So this is an important assumption, or one of the important concepts in rationalizability. So here we have the formal definition of rationalizability. In simple words, what it means is that, for example, if we consider just a two-player game, so for every action of player 2 that player 1 assigns a positive probability to, which means that every action of player 2 that player 1 sees likely to take place, that player 2 could play, her response should be such that it should give her the maximum payoff to player one's action, or player two's action. Meaning, if player one is playing any action a sub j, where j is denoting player one, this action there should be no other action that gives player one a higher payoff than a sub j for any action of player two. In the second sub bullet point of point 1, the z sub minus j denotes all the other players except player j in this case. Uh, One of the important things to be remembered about rationalizability is that an action is rationalizable if it follows the rules of rationalizability through the entire sequence of infinite beliefs. So when we discussed about a player believing that the other player believes that she is rational, a rational action should hold, or a rationalizable action should hold throughout this entire sequence. Like it should stay rationalizable throughout the entire infinite sequence of events. Also, every Nash equilibrium is rationalizable, but the reverse may not hold true. This is because a Nash equilibrium is also always a best response to another player's actions or strategies. And the reverse may not be true because, like we discussed earlier, uh, for the basic concept or the basic idea why rationalizability exists is because a Nash equilibrium solution may not always be found. But every Nash equilibrium always has to be rationalizable, since the justification for coming to a Nash equilibrium or playing a Nash equilibrium is that it is a best response to the other player's moves. There are multiple methods of solving for rationalizable games, but the one that we use in this video is called the never best response method. Never best responses are actions that are never best responses to another player's actions. As the name suggests, these actions are also called strictly dominated actions or strategies, and they should never be played. Because intuitively, if a player knows that there is some other action that could give her a better payoff than the one she is currently playing, she would be better off playing the other action than this one. So, by the basic definition of rationality, this player would never play this action that gives her a lower payoff than some other action, given a strategy of player 2 or a belief that this player 1 has on the strategy or move of player 2. So the third bullet point here gives the mathematical definition of a never best response. So an action A sub I of player I is a never best response for any strategy alpha I or any other strategy alpha I of player I if the payoff, which is denoted by the use in this case, so the payoff that player 1 receives by playing alpha sub I when the other players are playing their strategies A sub minus I is always strictly greater than the payoff she receives by playing the strategy A sub I for all the other players' strategies. So by intuition, a never best response should never be played. So the method that we follow using never best responses is called the iterative elimination of never best responses or strictly dominated actions. So like we mentioned previously, a rational player should never play a strictly dominated action because she knows that there is some other action that will give her a strictly greater payoff than this particular action. So by the assumptions of rationality, like we mentioned in the first couple of slides, a rational player herself does not play a strictly dominated action, and she knows, or she should not expect another player to play a strictly dominated action either, assuming the rationality of the other players. And the ad infinitum rule even holds in this case that every player knows that the other player knows that she is never going to play a strictly dominated action, and the sequence keeps going forth. So by these points here, we can say that no player is ever going to play a strictly dominated action, meaning we can get rid of these actions from the payoff matrix completely. Since we know that a player is never going to play this action, we can delete these actions from, or these strategies from the payoff matrix. So what we do is we follow an iterative process in which in each stage we look for actions that are strictly dominated, and since we know that these actions are never going to be played, we eliminate them. So we go through these rounds of elimination till we have some action or set of actions that remain that are never eliminated in through this process. So this tells us that these actions have to be best responses since they are never strictly dominated. These actions give the players the highest payoff that they can expect given the belief that they have on the other players' steps. So these actions, which are rationalizable, are those that remain no matter how many rounds of elimination we go through in this iterative deletion process. So we'll see what this iterative deletion is in the next. So here we have an example of an iterative elimination of strictly dominated actions. This is a two-player game, as we can see, where player 1 on the left has two strategies B and S, whereas player 2 on the upper side has three strategies that she can choose from B, S, and X. The boxes here, or the numbers in the boxes, are the payoffs to each player, where the first number represents the payoff of player 1 and the second number is player 2's payoff. So from the flowchart that we saw in the previous slide, for the iterative elimination of strictly dominated actions, we in each round we look for actions that are never best responses and eliminate them one by one. Or we can also go at the same time, but for simplicity here, let's consider uh, just one strategy per round. So if we observe closely in this game, we see that player 2's strategy B is strictly dominated by strategy X. So if player 1 plays B, player 2's payoff by playing B is 1, whereas she gets a payoff of 2 by playing X. On the other hand, if player 1 decides to play S, player 2 is again better off playing X because it gives her a payoff of 2 than playing B, which gives her a lower payoff of 0. So we can see that player 2 is never going to play B since it's strictly dominated player 2 strategy X always gives her a strictly greater payoff than playing B. So by the rule, we can eliminate strategy B here. So strategy B is never an option for player 2. Now what we have remaining is the four boxes that we can see in the game, and we know that these are the only boxes that are possible or that will be played in this game. So again, in this round, we look for any strategy that may be strictly dominated, and can you tell there is a strategy that I see here that is strictly dominated. So if we look closely, we see that player 1's strategy B is strictly dominated by strategy S, because the payoffs 0 and -1 are always lower than the payoffs 1 and 0 by playing strategy S. So in the next round, we eliminate the second strictly dominated strategy, which is strategy B for player 1, and that's gone. So finally, we have this game that is remaining, because we know that the other moves are never going to be played by the respective players. So we know that player 1 only has one move S here, and player two's moves are S and X. So between S and X, we can see that player 2's strategy S is strictly better than strategy X, since the payoff is strictly greater than the payoff from X, which is 3 is greater than 2. So in this final round of elimination, we can eliminate player 2 strategy X, because we know she is never going to play this strategy. So this is gone, and finally the only strategy that is remaining here is strategy S for player 1 and strategy S for player 2. So this is the rationalizable action that remains throughout the iterative elimination process, which means that this is the solution to the game here. And this elimination was possible because of the because of the assumption of rationality, because each player since she knows that the other player is going to act rationally, she would also know that the other player is not going to play a strictly dominated action. So we could eliminate all the strictly dominated actions, and finally the only solution that prevails is the rationalizable action SS. So this is the final outcome to the game. We can also use iterative elimination with weakly dominated strategies, meaning the strategies in which at least one payoff is equal to another strategy's payoff, and the other payoffs of that strategy are lesser than other payoffs. But for this video, we're just going to stick with strictly dominated actions, and another video is going to talk about weakly dominated actions for iterative elimination. So these are the references, and thank you so much, and you may refer to these to read more about rationalizability. Thank you.